All right. Hi, everyone. I'm Richard. I'll try to get to know your names as the course goes on. This is very little evolutionary game theory. I have a course repository set up that you can use to keep track of all the course materials. There are notes for this lecture already there, a PDF of notes that cover the material from the lecture. Nevertheless, it'll be in your interest to scribble down everything I write on the board for your own practice and education. Trust me. The goal of this course is to give you an introduction both to the concepts and the mechanics of evolutionary game theory so we can study, what's the way to put this, how evolution works when the best thing to do depends upon what other animals are doing. So the sort of historical introduction to this material and why it's so important for the study of evolution is that Darwin got it all wrong. Right, so in The Origin of Species, Darwin missed frequency dependence completely. He missed the fact that the best thing for an organism to do will often depend not just upon the physical environment, but upon a dynamic social environment. He fixed that in a later book, right? In the first book, he missed it completely. And this is not a small omission, because there's a bunch of weird stuff that happens in evolution as a consequence of this. Like, for example, that natural selection doesn't necessarily produce adaptations when there is frequency dependence. Yeah, it can lead species to evolve to extinction. And this is a big problem for conservation biology. Obviously, this is something to worry about. Those of us who study human evolution, we worry about this too, because primates, humans, are extremely social, and there's no guarantee that social evolution will be adaptive. So that's the bait. So over 5 lectures, I'm only going to give you 5 lectures. I want to go through sort of the top-level topics at different levels of abstraction, just to give you an idea how game theoretic models are constructed and manipulated. So this first lecture, we're going to study the evolution of conflict. This is a good place to start because the classic models of the evolution of conflict are very simple. So I can show you what game theory models look like and we can solve them without needing anything more than a little bit of high school algebra. In the second week, we're going to do cooperation. Cooperation and coordination. Which are really just a different perspective on conflict. Because the whole reason we study cooperation and coordination is that there's conflict in the attempts to create cooperation. So there will be a mathematical isomorphism between what you're going to learn today and what we'll do next week as well. But there'll be a kind of mental shift when we think about it differently. I should say that just as a teaser for this, coordination is really difficult. It isn't like it's some easy thing. So we often say coordination is simple, but coordination in nature is often a very, very difficult problem for organisms to solve. In the third week, I'm going to do what I call the evolution of relationships, which is when animals meet more than once, and they can use memory of one another and what they did to one another in the past to regulate their own behavior. In the fourth week, we're going to study the evolution of families, by which I mean, the biologists here expect, inclusive fitness and other fun things like that. For anthropologists, families mean way more than inclusive fitness, and I might say some stuff about that too, but it depends upon the amount of time. Well, look at some people who got snacks downstairs. And then in the fifth week, scale it all the way up and talk about the evolution of society, by which I mean there'll be cases where there's structure to the society that affects how social behavior evolves beyond just the existence of humans. That's the goal for the 5 weeks. So I think we do the first 2 lectures and then there's fall break. Yeah, I pause during fall break because I'm a parent. Right, so I pause during fall break, and then we resume after fall break, and we finish it up. Okay, but the calendar is here. If you ever have doubts, go to the course website and check it, and I'll keep posting notes there. Okay, I assume there's no questions so far, but if there are, make a bodily motion, and I'll call on you. Okay? No? If you have a question while I'm scribbling at the board, I have a tendency to like stare at the board and write. You should just make a noise and get my attention. I'm happy to take questions. I think it's a virtue of teaching a chalk and board class is that I can be responsive to your needs. Yeah, if I had slides, that means you don't exist to me, right? I'm just going through the slides. And so I don't do this course like that because I'm trying to keep pace with what you understand and not move faster than that, okay? So the more squeaking you make, I look at my own PhD students who squeak at me constantly. It's more like yelling, though, isn't it? They demand things from me and I respond, right? No, you nod. No, it's the point of the chalk and board class is that I can be responsive to what how the students are doing. Okay, so for this first lecture, we're going to start with the evolution of conflict. Yeah, let me write this up here. And this gives us a chance to build a really basic game theoretic model so you can see in a stylistic sense what game theoretic models are like. And as, I don't know, I guess as a bit of a prelude to what I'm going to try to demonstrate to you today is that game theory is incredibly stupid. By which I mean, when you see the structure of a game theoretic model, you're like, this is unbelievably simple. The real problems we study in biology are much more complicated than this. And the game theoretic model is stupid. It leaves out a bunch of stuff. And that's by design, because if it weren't stupid, we couldn't analyze it. Yeah, we can't analyze nature. Nature's a mess. We're a mess. We're part of nature, right? So we make this little stupid world called game theory that we can analyze. And we can answer questions about why it functions the way it does. And we learn stuff from these little stupid models. So even though it's in its constitution, as it were, game theory is stupid, it teaches us that we're just as dumb, right? Because it's very hard to anticipate the consequences of the dumb little model. But I'll show you how to do it. We use logic. Once we've got the simple model, we can use logic to extract insights from it. And often they're very surprising. People have a hard time, everybody, including myself. I've been doing game theory for 20 years, and it's very hard, even in really simple game theoretic scenarios, to anticipate what will happen, and that's why we need the logic. And then we take the lessons from different game theoretic models, and we apply them qualitatively to natural phenomena, or we make more complex, bespoke models of particular systems. But in this course, we're just going to stick with the very stupid stuff, right? But I know it will be valuable to you, because I've taught this sort of course many times. Okay, the scenario in the evolution of conflict that goes back really to the 1970s in evolutionary biology is the observation, of course, that there are resources that animals want and they don't want to share. These can be territories, food items, mates, any number of things. And so we start with the principle that there's a non-divisible resource. Divisible resource, and it has some value that I'm just going to label V, which is just the variable V, and this is some fitness value to the organism. I'm going to be vague right now about what that fitness value means. You can think of it as extra offspring in a very simple life history. And pairs of individuals can test this resource. So they meet, the resources between them, and they have to decide what to do. And we're going to make this, again, the stupidest game theoretic model. This is the classic from the 70s. Suppose that there are only two behavioral options in this contest. And these are behaviors right now. We're not talking about strategies yet. That'll come later, and I'll make it clear what that distinction means. We're just talking about behavioral options. What can the organism do? And the first option is to fight, which means the organism has some natural weaponry. It has claws and fangs and venom or whatever else it has. Yeah? And it's going to use those weapons to its best ability to drive its opponent away, injure its opponent, whatever is necessary, so that it can claim the resource. Yeah? The thing about fighting is that it can inflict injury on the opponent. And so the cost of injury is going to be little c. And this will be a deduction in fitness. It's an injured individual. Yeah? Clear so far? I told you it'd be stupid. Yeah? Yeah. It gets more interesting. Trust me, this builds. Alright. The second behavioral option is to do some sort of ritualized display that does not risk injury. And I'm just going to, this is usually called in literature just the display option. But it can involve play fighting. It's like wrestling, right? North American biologists know a lot about rattlesnakes quite often. Rattlesnakes, people here know what rattlesnakes are. So rattlesnakes are interesting. They're all over the Western North America. I mean, everywhere. Like in your backyards, every place there are rattlesnakes. They're indestructible. They're every place. Every pile of wood has a rattlesnake under it. Rattlesnakes like to eat snakes because snakes are like prepackaged snacks for a rattlesnake, right? It's just the right shape, exactly the right shape. And but when rattlesnakes meet one another, they don't try to eat one another usually, unless there's a big size difference. Instead, they wrestle. Now they have fangs and they have venom, but they don't use that when they fight one another. Usually they fight over territory. Instead, they wrestle, and it's a really funny thing to see, two snakes wrestling. And then eventually one of them leaves. We don't know why. Gets tired, bored, hungry, something. Gives up, cedes the battleground to the victor of the wrestling match. Why should rattlesnakes wrestle? Well, this is what this model is trying to answer, is why would a creature with vicious natural weaponry like fangs and venom, and rattlesnakes can be poisoned by their own venom, right? If they're inoculated with it. Why would they instead do a display, right? But the display includes things like wrestling. That's what I want to make clear. But there's lots of animal societies that have these kinds of ritualized combat, right? So like elk fighting with their antlers. They're not trying to kill one another with their antlers. If that was the case, they'd charge at the side, they'd ambush, right? Yeah? Which they do sometimes do when they're fighting predators, right? When an elk fights a predator, it tries to kill it with its antlers. When it tries to fend off another male, it does something different. Yeah. Does this make sense? Yeah, I appreciate not everybody here has the same sort of watching nature documentary childhood. Right. Okay. But it could also be just a dance or anything else that goes on. Yeah. Okay, those are the behavioral options. So to figure out what sorts of behavior will evolve in a population, we have to talk about strategies instead. And strategies, these are heritable behavioral programs. So we're going to start here, as I said, with the stupidest game theoretic model, and the strategies will simply be the behaviors I just listed. Yeah? They'll get more complicated though. We're going to have contingent things. Strategies can be very sophisticated. They can also be random. Yeah? Random is a program. We'll have all kinds of things like this in the 5 weeks, you'll see. And when we get to relationships, right, there's going to be highly contingent programs that use memory about how people treated you in the past. So we're going to consider only two strategies to begin today. The first is called hawk So this comes from political science, this terminology, right? Hawks like to fight. I don't know if they actually do, but this is the political science term. It's hawk. Hawk always fights, which means it risks injury. Yeah. Good? I know this one-to-one mapping of strategy behavior is a little weird because it seems redundant, but it'll pay off in a little bit, trust me. And the second strategy is called dove. Again, this is a political science term used from international relations. Doves like peace, right? I don't know how this association came about. And doves always display. So now we've got three kinds of interactions. And I'm going to lay out for you what happens in each of them. Then we're going to actually figure out algebraically what natural selection would do to the proportion of the population that is each of these strategies if these were heritable. That is, if offspring resemble their parents, and we count up the V's and C's as the consequences of contests, and we figure out what would happen in a population, a large population of hawks and doves over time. That's the goal. Okay? So three kinds of interactions. First one is hawk, hawk. So say two hawks meet. Now they don't know they're hawks, right? So they don't assume there are organisms that can genotype other organisms in their society, but that's not what this model is, right? Yeah. Cnidarians can do this a lot, right? Those of you who know aquatic organisms. But we're not imagining a model like that yet. It's just two individuals meet. Hawk is their program, so they both fight. Yeah? So they both fight. Now what happens? Well, both attack. Each risks injury. And we're going to assume that the loser, the winner gets the resource, obviously, right? Winner gets B. And the loser has one of them. Yeah. Yeah, help me here. I am a native speaker in English, I just can't spell. Yeah. Loser.
No, one. Two is looser.
Two O's is looser. Yeah. Yeah. I will make a mistake and you should call me out on it eventually. Yeah. It's minus B. Now the question is, which individual is which is just a coin flip from our perspective. Of course, there are differences between the individuals that determine who wins, but we don't have any information about those things like fighting ability. So from our perspective as a modeler, it's completely random which individual wins, because all random means is we don't have any information that can predict the outcome. So it's a coin flip because which individual is number one and which individual is number two is arbitrary. Right? It's like red shorts and blue shorts in Olympic judo. It's randomized, or at least you hope it is. Yeah. Because wearing red shorts makes you stronger. Everybody knows that. Right? And so there's just a half chance for each individual that they're the winner or the loser. And so then I'll summarize the consequences of this in a little table in a moment, but I want to move on to the next interaction first. But does this make sense? Just the consequences of our assumptions here. The second type of interaction is hawk-dove. One hawk and one dove meet. The hawk attacks, brings out its natural weapons. The dove does a little display, and then it gets attacked, and then it retreats. So the thing about the dove is it's not willing to escalate. It's not willing to risk injury. That's the whole point of the display, is it doesn't want to risk injury. Okay? So in that case, the hawk gets V, and the dove gets nothing. And that means no change in its fitness. These V's and T's are changes in fitness. We have to assume that these animals are doing other things like eating, right, which is impacting their fitness. And this is just one little micro interaction in their lives. Yeah. Does it make sense? So the zero doesn't mean dead. It means nothing happens, right? And then finally, we've got how am I going to do we've got the third kind of interaction, which is dove-dove. Two doves meet. They both display. They do their wrestle, their dance, they lock antlers for a bit, whatever it is. One of them tires out first. However you decide who wins a wrestling match, someone gets pinned, right? Something like that. We still have a winner and a loser. And the winner gets B, and the loser gets nothing, because they don't get injured. And again, which is the winner and which is the loser is random from our perspective, which isn't to say that it's really a coin flip in nature. It's just to say that the aspects of the competitors that determines who wins, we don't have information about that yet in this model. Okay? If we have enough time today, I'll show you a model where we do have information about that, like size, and then we can add that to the model. But right now, it's random from our perspective, which just means we have no information to predict it, so each dove has a half chance of being winner from our perspective. Good? If it's not good, you should say so. Yeah? Okay. That said, those of you who know me, you know I say this every time I teach class. Not understanding everything is fine. That's a weird thing for a teacher to say, but there's a lot of moving parts to this sort of material, and most people don't understand it all completely the first time through. But that's okay. All you need is to understand enough that you can keep moving forward, and then you can come back and revise the things that you didn't get completely the first time. And that's why there are course notes and everything, and we can work through it. Yeah, you just need to be able to keep up with the narrative. Keep swimming forward, yeah, like a shark. Yeah. Okay. Okay, what have we done so far? Let me recap. So we set up our scenario. We have a question. When there are non-divisible resources and animals want to claim it, they have a pairwise contest. The basic motivating question is, why is it that these sorts of displays exist? Yeah, animals have natural weapons, but when they fight conspecifics, members of their own species, often they don't use them. Why is that, right? Like when lions fight. Yeah, lions are much more vicious with their food than they are with one another. Yeah, I have a house cat. Anybody else here have a house cat? You know that house cats fight constantly with your ankles, right? This is the thing that they do, but they're much more vicious with real prey than they are with your ankle. Yeah, if you've ever watched this. And so this is the basic motivating natural history question. When would natural selection favor these displays? When would it favor all-out fighting? Because there are species that do the all-out fighting. That does happen as well. And this motivates this very basic, I keep calling it stupid model, two variables, B and C, to keep track of, the value of the resource, the cost of injury, define two possible behaviors, two possible strategies that map directly onto them, just to keep it simple to start. And then we take the interactions between these strategies and we define what happens in each case, and that's what we've done so far. So now I'm going to summarize these three types of interactions with something called a payoff matrix. So what we do is we imagine we've got some focal individual, and that focal individual can be a hawk or a dove, and there's an opponent. And that opponent can also be a hawk or a dove. And this gives us a little matrix. And in this matrix, we're going to write down the fitness consequences to the focal individual of each interaction, just to summarize what we did here. So this is much easier to do. And what I'm going to teach you to do is you can use this matrix to solve lots of things about the evolutionary dynamics of this game, basically just by using your eye brain, by looking at things. But I have to teach you how to do it, okay? There's other stuff that the matrix is not sufficient for, and I'll show you that too, but there's a lot you can do just with the matrix, at least for this type of game. Okay, so when hawk meets, I told you there's a winner and a loser, there's a half chance of each, so the focal has a half chance of winning, so half the time he gets V, and the other half of the time minus C. So the expected fitness consequence to the focal individual is half V minus half C. Yeah. You have to imagine there's a bunch of these interactions with hawks fighting hawks. What happens on average to a hawk in such pairs? That's what they get on average. Yeah? And so that's what natural selection will care about on average. What about hawk and dove? Well, the hawk always wins, right? And so the hawk gets V. Now the dove. You're a dove now. Yeah, good for you. And dove meets a hawk. What happens? You bravely run away. Yeah? Very wise. Yeah. Two doves meet I wrote the consequences up here. The focal individual will be the winner half the time. And the other half of the time you get 0. Right? Because you retreat, because you don't get injured. Yeah, question?
Sorry, is the 0 like 0? Or is so it's
0.
It's just half V.
Just 0.
Yeah.
Yeah. I'm putting a dot in it so it doesn't look like an O. Yeah, I don't know if this is confusing people more. This is like a chalkboard convention. Yeah, Cody likes it. Okay, good. Yeah, it's a 0, and it means no fitness change. There's no fitness change as a result of this interaction. There's lots of other stuff happening in the animal's life, so it's accruing fitness through other stuff, but that's baseline average fitness independent of this scenario. Does that make sense? That matters because I'm not going to draw that out too much in this lecture, maybe in a later lecture. Effectively, we're assuming selection is weak because there's a bunch of other stuff going on in the animal's life that matters. Once you start studying other topics like sexual selection, so if you want to model the evolution of peacock tails, you can't assume selection is weak because being able to reproduce is kind of a bottleneck. Right? So, but that's not what we're doing with this. We're assuming this is a non-lethal interaction. You suffer some injury, you get a snack, something like that. But effectively, we're assuming selection is weak, and that makes the model easier. This will come up in a later lecture, but we don't have to worry about it too much now. Okay, good with this? Yeah, question.
Earlier, you gave the example of 2 rattlesnakes wrestling, and you classify them as display. But there's a very real risk of injury, and there's expenditure of energy. So how would that classify as a display instead of a fight?
That is an excellent question. If I understand your question right, is in the displays, of course, they're using energy to wrestle, and that is a cost, and I haven't modeled it here. And that's an excellent question because that will be your homework problem, is to add that to this model and derive the consequences of displays having energetic costs. It's fun. Okay. I promise you, it's fun. If your idea of fun is like mine, doing algebra. Okay, are you guys with me so far? Yeah? With this? Okay. We're going to ask 3 questions of this model. First question. When can hawk or dove be evolutionarily, how's that for a word? Stable. And some of you may know this term of art, evolutionary stable strategy, ESS, and this is what we're talking about here. We're going to ask when hawk or dove can be an ESS, an evolutionarily stable strategy. What does that mean? That means if you had a population that was entirely hawk, and you imagine you're God and you mutate a hawk into dove, what's the consequence of this mutant dove? Will it tend to increase in frequency in the population, or will it tend to flip out again? That's the question we're going to ask. We're going to ask it for hawk, and we're going to ask it for dove. For dove, it's a population of doves. Put in one hawk, what happens? A strategy is evolutionarily stable if, when it's common, it can resist invasion by a rare alternative strategy. Good. I'll say that a bunch of times during the lecture, so if you didn't get it, that's fine. You'll have lots of chances. The second question we're going to ask is there any stable mix of hawk and dove? It's possible that you can have hawk and dove coexisting at particular proportions in a population because there's stabilizing selection. The biologists here will recognize this term. This means that selection tends to favor some particular proportionality between the different strategies. We'll address that too. It can often be true in evolutionary models that you can have ESSs and you can have stable mixes. Yeah. In complicated, less stupid game theoretic models, there can be lots of possible mixes that can all be stable, right? So you can have lots of fun. This will be easy. It will not be like that. But just to give you an idea that this is, it's not unusual to have lots of stable mixes of things. And then the third question we're going to ask is, what is best for the species? Which is a very vague question, right? It's almost philosophical. We're going to make it simple and stupid and say that this question here means what proportion, what mix of hawks and doves would maximize the population growth rate? And we can answer that, at least heuristically. Yeah. I know this is a very special and weird definition of what's best for the species, but this is what we're going to go with. If you can maximize the population growth rate of the organism, that'll probably reduce its risk of extinction. Yeah, it's not a bad guess. Okay, you ready? We're going to answer these one at a time. At some point I'm going to have to loop back and start racing over here. Yeah, but that'll be my cycle, we'll see. Like a robot that writes from left to right and then starts on the left again. Okay. So let's start with question one. To answer this, you could really just stare at the matrix here. So let me show you how to do this. The way to think about it is, there's a population of hawks. And the first thing to figure out is, well, what are the hawks getting when they're common? And that's hawk, right? So this is what hawks get when they're common. Yeah? So that's what we say, is when hawk common, each hawk gets, on average, I'm going to start writing this v minus c over 2 because it lets me write 1 less 2. I'm lazy. Okay. Yeah, it's the same thing. This is also, I know that if you're a normal, psychologically healthy person, you have not done algebra in a very long time. Yeah? If you're like me, you just do it at home for fun. Yeah, get an idea, ooh, I'm going to make a model. Right, that's like after dinner entertainment for me. But for normal people, yeah, you would not do this. This is also a way to slowly get you, I know it's in there, right? You've all finished secondary school. So you could do algebra, but maybe you're a little rusty. That's fine. It'll come very rapidly. Now we have to ask, to figure out if hawk is evolutionarily stable, what it gets when it's common needs to be larger than what the rare strategy gets facing the common strategy. I'll say that again. For a strategy to be evolutionarily stable, what that strategy gets when it's common, that is against itself, needs to be larger than what the rare strategy gets against the common strategy. Right? Why? Because the rare strategy, in this case dove, is not going to meet itself, at least not very much. And so the impact of interactions with itself, dove-dove interactions, initially are negligible. They don't have any effect on the evolutionary stability of hawk. Yeah? For dove to invade, it needs to do better against hawk than hawk does against itself. Does that make sense? Okay. And we can see this in the table too. So, you're a rare dove, and this is what you get. Make sense? Easy, right? So, the condition for hawk to invade, for hawk to be in ESS, hawk is ESS when V minus C over 2 is greater than 0. And always with these things, so your natural reaction should be, okay, exciting. Always with these things, we want to reduce them down to the simplest algebraic form, right? So that we can read them philosophically, get some kind of qualitative insight about what it means biologically. So in this case, we can simplify this, yeah? This simplifies to V greater than C. Because if V is greater than C, then the left is positive, and then it's greater than 0. The 2 doesn't matter. Yeah? Or you can just pull up your high school algebra, right? For those of you who keep doing it like me, it's simple. You multiply by 2, the 2 goes away, and then you add the C. Yeah. Good? Having fun? Okay. Okay. I broke my column. Okay. Good. So, this is a condition. What this means is, hawk is not always evolutionarily stable. But if the value of the resource is larger than the cost of injury, it is. A rare dove cannot invade. Yeah? Natural selection says it's worth fighting. It's not worth displaying in that circumstance. A rare dove can't invade. Make sense? We also need to, if this is not true, if your natural weaponry is quite dangerous, like a house cat, yeah? Remember, house cats have claws that are the length of their feet. They just don't usually extend them, right? They're monsters, tiny little monsters, yeah? And so C is large in the domestic cat. And in that case, the value of the resource, if it's just something like a food item, is not likely to be larger than the potential cost of injury. And in that case, a rare dove can invade. Because even though it never wins the resource, it also doesn't get injured. And then doves can increase. Does that make sense? I told you it was a dove model. But this is not obvious from the assumptions. I mean, hopefully you feel a little burn of learning, right? That you're learning something. It builds, trust me. So we also have to ask the opposite for doves, right? Or the same thing for doves. When is dove in ESS? And we do the same kind of thing with the matrix. So dove against dove. When doves are common, they always face other doves, and they get V over 2 is how I'm going to write that, right? That's what doves get on average. That's the change in their fitness as a consequence of the contest. Yeah? And this term goes away, and that's V over 2. That must be larger than what a rare hawk gets. And what does a rare hawk get? Just look it up. You're a hawk now. Now you're in the dove column. Yeah? When dove is common, the only thing that matters is the dove column. When hawk is common, the only thing that matters is the hawk column. Yeah? So we're in the dove column, you get V. You probably don't need to do any algebra to know that this is never satisfied. But, since I'm a pedant, I would like to point out that it can be satisfied if V is less than 0. I told you I was a pedant. Yes. So, which makes no sense given the whole foundational narrative of the model. if the value of the resource were negative, that means you'd be fighting over an electrical outlet or something like that, right? Something that would hurt you. People do that, but I like to think other animals are smarter. Yeah. So we're going to say that this is never satisfied. Yeah. Just because the scenario we're interested in assumes that there's a positive fitness value to the resource. It's not poison. Okay? So dove is never an ESS. Hawk can be an ESS, but it may not be. So if it's not, so here's the situation we're in now. We're ready to move to question 2. Right? We just did question 1. We're ready to move to question 2. If B is less than C, if B is greater than C, then we're done. We know what happens. It's an all-hawk world. Yeah, but it depends upon the B's and C's. If B is less than C, neither strategy is evolutionarily stable, which implies something happens in the middle. There's a mix of them, some mixed dynamic that we need to derive, and that's question 2. So to figure out question 2, we've got to write down an expression now for the average fitness consequence to a hawk and to a dove of existing in a population in which there are different proportions of hawks and doves. So I'm going to introduce a new symbol now for that proportion. I'm going to let the letter P for proportion be the proportion of hawk in the population. So that the invisible assumption here is that the population is large enough that we don't have to count individuals. Yeah, it's a big population. There are thousands of individuals interacting in pairs, and so we can just use the proportion. We don't have to worry about finite counts. Yeah, make sense? If you wanted to do finite game theory, we could do that some other time. But that matters on things like if you want to do game theory on graphs, on social networks, then you usually can't do these proportions. But this works for our stupid model. That means that 1 minus p is the proportion of dove. Yeah, because there's only 2 types. So we only need 1 symbol. And then we can write an expression for each strategy, hawk and dove, of what it would expect across all the pairs, right? So you put yourself in the shoes of a dove. You haven't entered, you've just arrived at a pair. You don't know the strategy of the other individual. Yeah, and you can't find out. All you know is their behavior. Well, you're about to find out, I guess, because behaviors and strategies are the same in this game. But if you're going to bet, you're a betting dove, right? What would you bet is the probability that your opponent is a hawk? Well, if you knew the proportion of the population that was hawks, that's what you should bet. Yeah, and that's P. So we can write an average expression. So we're going to write this. The average fitness of dove. P is the time you interact with a hawk. And then what happens? Audience participation? No? I will train you. Oh, yes, I will. You run away bravely, right? Because the hawk attacks. And you're like, oh, hell no. And you're out, right? So you get 0. Yeah? Which doesn't mean you're dead. I'll keep saying this. It means there's no change as a consequence of the interaction. The other thing that happens is 1 minus p at a time, you meet another dove. This is the alternative. And then what happens is you have a little display contest and you win half the time. So you get v over 2. Right? That's here. Right, so these are the 2. It's just that this happens p at a time, and this happens 1 minus p at a time. Right, before we were in only one column. When hawks are common, you're only here, and all that matters is the 0 for a dove. When doves are common, you're in this column. Now both columns are in play, but it's like this column is weighted by p, and this column is weighted by 1 minus p. And so we write mathematical expressions that add those two weights together. Right? Why? Because the axioms of probability demand this is how you calculate an average. Yeah? Remember that if there are two alternatives, you add. If things happen together, you multiply. If things are independent events, you add them. Yeah, you learned this once upon a time. Yeah, I know you did because you finished secondary school. Yeah, and then you went on to better things. I know, but it's my job to take you back. Yes. So this is our expression p times 0, which is of course 0. You can ignore this term, and 1 minus pv over 2. And this is the expected fitness change of a dove in a population in which p of the individuals are hawks. Good? I told you, it's a stupid model, but you start building it and interesting things start to happen. We also need an expression like this for hawks. And that's going to be p times what happens when a hawk meets a hawk. Yeah, they fight. Someone wins, someone gets injured. So, b minus c over 2. Or, the hawk meets a dove. Right? Hawk meets a dove. And wins the resource. That happens 1 minus p at the time. Now the question is, what do we do with these expressions? Well, we want to figure out the evolutionary dynamics. Now, if you're going to be a rigorous evolutionary biologist, we have not, or it's the royal we, I have not said enough about population regulation or anything for us to derive the evolutionary dynamics. So for example, I haven't mentioned parental care. If you have more offspring, do they die? Right? There's tons of weird stuff that could happen, right? Could. Most game theory, you ignore all that stuff because it's a philosophical question. If natural selection could get its way, what would it do? And there's lots of reasons that natural selection doesn't get its way in real populations. Lots of them, yeah. But that's not the question we're asking with this model. We're asking if these fitness consequences could be transmitted towards changes in gene frequencies, what would happen to gene frequencies over time? And that's the question we're asking. So in that sense, we can answer the question, what happens to p over time, because we can just heuristically ask, which of these is bigger for each value of p? I'll say that again. Which of these expressions is bigger for each value of p? You ready?
Excuse me, Richard.
Yes.
I need if you can go back for clarification about the second question. The relationship between the matrix and how you are making the second question.
So this question.
Yeah.
Yeah, well, we haven't answered it yet. So the idea is, to answer the second question, I've got to write these two expressions. And each of these expressions is the average fitness of each strategy. So this one's for dove. The dove strategy is in a bunch of doves. So we've got a big population, and there's a bunch of doves. Some of those doves interact with hawks, poor things. They get nothing. Some of those doves interact with other doves, and some of those doves win the resource, and others, but none of them get injured. On average, across all those doves, so if we had a big population of doves, and we just censused them, what were the consequences of their contests? And we averaged the fitness consequences of those contests. This is the mathematical expression for that average. That's what we're writing down. Does that make sense? Yeah, you could do it empirically. If you were a field biologist and you were going to actually do this, that's what you do. You go like, what are the fitness consequences of the interactions? And you write it down. And if the theory were right, you'd be able to approximate it with an expression like this. Does that make sense? Same thing for hawks. There's a bunch of hawks in the population. Some of them interact with other hawks. They have fights. Some of those hawks get injured. The others win the resource. Some of the hawks interact with doves, so they get the resource. We census each hawk. We figure out its fitness, and then we average this is the mathematical expression in theory that gives us that average. And these averages are what's relevant for determining what natural selection would do, because it's the average fitness of an allele that determines whether it increases or decreases, right? Well, it's the relative average fitness. Yeah, I'm skipping a bunch of biology. There's a 10-week version of this course in which I start with population genetics. It's the first week, and then we get to game theory in the second week. I'm skipping all that. So this is like cartoon evolutionary dynamics here. I apologize, but you can ground this in like real genetics and stuff. Of course, when we think about primates, we think a lot of these strategies are learned, right? And there's a bunch of social learning theories that can also give you dynamics in this, but I'm skipping over that as well. Are we ready to move on? If we're not, you can just tell me to stop. Yeah? I'm just going to keep pace with you. There will be a break, by the way, if you want to stand up and take care of biological necessities or something. Yeah, but I'll try to break at the hour. Okay. Okay. It's not the greatest eraser. Okay, so let me do this heuristically for you. Let's think about it. Remember, the question is, which values of P, which proportions of Hawk lead the fitness of Hawk to be greater than the fitness of Dove? Let's ask that. And so the expected fitness of Hawk is P minus C over 2 plus 1 minus PV greater than, I'm going to simplify, right? So this is Hawk on average across a bunch of Hawks, right? The Hawk strategy is in a bunch of bodies. Those different bodies have different experiences, but on average, this is what they experience. With me? I appreciate how rude this is. And this is nice. And I've just dropped the term that has a 0 in it because who cares about 0? Yeah. Applied mathematicians love zeros. Got a bunch of symbols, pick one and make it 0. Yeah? If the relative values are all that matter, just removes a symbol from your math, cancels a bunch of terms, it's genius. Right? Mathematicians hate this one weird trick. Right? It's the sort of thing. Okay. So we can just simplify this. Yeah? And ask, right? This is a mathematical question. This is what I love about algebra, right? It's like there's this transition, you go from arithmetic in grade school, and it's just like, what is this? It's like a way to balance books and figure out how much a hot dog costs, or what is this for? Yeah, it just seems crazy. And then there's algebra, which is this world. It's a general system for solving questions. If you state any question, it can tell you whether it's answerable, yeah, and how to answer it. It's an amazing invention. Yeah, really extraordinary thing. You can tell I'm a dork. Yeah. This is all true, though, that I'm a dork. Yeah. No, that algebra is a powerful way. So this is a question, right? And we can reduce this system. There are rules that you learned in secondary school. We can reduce this system to make this, to see what the answer to this question is. And the question is, when is this, which values of P make this true? Yeah, so the way to do this is to isolate the letter P on one side. Yeah, we did this, right? Nightmares returning? Yeah? Yeah. Okay, so there are lots of ways to do this. I'm going to start by just getting rid of the 2's because fractions offend me. Yeah, I do not like them. Question?
Sorry, is this for evolutionary stability of the Hawk? Is this what we're trying to calculate at the moment?
We already did that. Evolutionary stability of the Hawk is here. Okay. We're assuming now Hawk is not evolutionarily stable.
Oh, okay.
And we're asking what happens. And so what we're asking is, what are the evolutionary dynamics at each value of P? So you want to imagine that there's, well, let me draw it out. So you've got some spectrum, and right, and this is P between 0 and 1. So this is the all dove world, where there are no hawks, and this is the all hawk world. We're assuming, because V is less than C, that dynamics increase hawk on this end, right? A rare hawk invades, that's what this little arrow means, and a rare dove invades over here, because V is less than C. So something happens in the middle. So for every point on this line segment, we want to ask whether the evolutionary dynamics are pushing this way or this way. And so this question is, which values of P push you this direction? Does that make sense? Yeah. Okay, and we can answer it. So the first thing I do is I get rid of the 2's. Yeah, group the P's. Exciting to watch me do algebra, I'm sorry. But I thought he was loving it. Yeah, that was very good. Fake, not funny. Okay. We got -2 P's, yeah. And then there's one over there I gotta bring over here, that's a plus V. And we got a V there and -2V. Someone wanna check, make sure I did it right? There's this phenomenon that math instructors know called blackboard radiation. The closer you stand to a blackboard, the dumber you get. And I'm standing very close to this blackboard right now. And so I will make algebra mistakes, and it is your job to laugh and point and go, ha! Yeah, but I think I'm okay. Did I get this right? So we've got 2 V's and -2 V's, so all the V's cancel. Yeah, and that's -V. And so this is, you ready? There's a trick involved here. We're about to divide by a negative number. That face is great. I make that face all the time, so I appreciate it. When you divide by a negative number and you have an inequality, you got to flip the inequality. You learned this in secondary school. Yeah, it's like a trap that math instructors create for you. And so this becomes P less than V over C. So for all, so what does this mean? There's some point on this line segment, say right here, which is V over C. So say V is like 2 and C is 3, right? Then it's at 2/3. Yeah, that looks like 2/3? Yeah, that looks like 2/3. And so what we just said is that for all values of P less than that, P is increasing. You with me? This is science. Now, I joke about this, but these insights are hard fought, right? It's very hard to make clear deductions about scientific questions unless you do a little bit of formalization.
But
Yeah,
the assumption is that P is increasing over some time, generational time.
That's
yeah?
right.
Okay.
Over generational time. And we haven't specified anything about generation length or any of that stuff. This is purely heuristic.
Yeah.
That's absolutely. Is there another hand? No. But we could write a simulation. You could write a simulation that puts all those details in, and then you could talk about how long it takes to reach equilibria. And sometimes that's really useful because there are games, I think after our break, I'll show you one actually, where there are transitional dynamics that can be really slow. And the system spends almost no time at the endpoint equilibrium. It spends all the time in some slow drift phase. And so evolution is much more interesting, right? This is this thing I call post-Darwinian evolution, right? All the stuff Darwin missed. So all these transitional dynamics, especially once you get to stuff like community compositions. And anyway, I'll stop talking. But I like the fancy stuff. So we could ask the other question. I'm going to spare you the algebra. Just imagine flipping the inequality up top, right? And that asks the other question: when is dove increase, right? Because if hawk has a lower expected fitness than dove, then we just flip the inequality, right? Just flip all of these inequalities. Yeah, so now less, 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 greater. Yeah, all the algebra is the same. And now what we say is dove increases whenever P is greater than V over C. Here's V over C again, and so all of these points. Dove increases, which means P gets smaller. Good? Which implies there is only one value for the proportion of hawks that is evolutionarily stable, that is an endpoint of evolution, and that is at V over C. Yeah, which obviously requires that V be less than C, otherwise this is off the end of the, right, this is the all hawk world. As V increases, this point moves to the right until it hits 1, and then hawk is an ESS. Yeah, as soon as V is greater than C. If as C increases, the cost of injury increases, this point moves to the left, and you get more and more doves, because fighting is really stupid. Right? Good? Does this make some sense? Okay, with that, I think we should take a break. Yeah? And why don't we take 10, so you can stretch and go to the restroom if you so desire, or get a drink of water. And when you come back, we'll do question 3, and then I'll introduce another strategy that will upset everything. Okay? Okay, what's that? So, where were we? We had answered question 2, right? What mix of hawks and doves could be evolutionarily stable? When V is less than C, there is a unique evolutionarily stable value of the proportion of hawks at V over C, which represents this trade-off. At that point, these two expressions are equal. Right? So if you replace P with V over C in these expressions, the left-hand side and the right-hand side are equal. I leave that as an exercise to the student. And during your lunch hour, you can get out some paper and do that yourself. Yeah. But I insist it is true. It is. And that means that this is what's called an equilibrium. The value of PV over C is an equilibrium value at which the expected fitness of all the strategies is the same. And so the population isn't changing under the influence of natural selection. There are other forces, I'm going to keep saying this throughout the whole course, there are other evolutionary forces than selection. Yeah, you've heard of some of them. Yeah, they all matter. And most of them are very powerful as well. So migration, for example, is a force of evolution, and it's extremely powerful in animal populations. We're neglecting that until the last week, when I'm going to dazzle you with a migration model maybe and show you some fun stuff. But when we have population structure and migration, I think for ecologists that's a very important sort of thing. Yeah. But right now we're saying all those other forces are negligible. Mutations only happen when we throw in a mutant and things like that. Mutations can be biased. Tons of fun things can happen with mutation as well. We're ignoring the fact that any genetic architecture which would produce behaviors like this is going to be highly polygenic and complicated, right? Just ignoring all that. Right? Heritable, it's just heritable. Parents that resemble offspring. It's not because we don't believe those things matter. It's because we're asking a qualitative question, what would natural selection do, right, if it got its way as a consequence of these behaviors? This is why these models don't make quantitative predictions necessarily, but they do make qualitative predictions about how systems behave. They answer general questions. And qualitative answers are what scientists usually really want. I'm going to say that again. Qualitative answers are usually what scientists really want because they're generalizable in a way that specific quantitative predictions are not, right? And I also teach a statistics course, and as all of you know, when you do data analysis, a tiny quantitative difference is not what you're looking for. You're looking for some big qualitative difference. Yeah, that's why this thing's significance was invented, right? For people to convert quantitative results into qualitative results. And some of you are laughing because you know my opinion about that. But that's just an example of what I do. So when I say something is a qualitative result, that isn't to say it's bad. Qualitative results are usually what we're after because they have generalizability in a way that quantitative results usually do not. Okay, so now we've got our third question that we need to answer here. And that is there some value of P, the proportion of hawks, which is best for the population growth rate? And what do I mean? We look at this spectrum again. Which value of P, if we could just stick the population in any particular place along this line, would maximize the rate of growth in the population? What that means in the little microcosm of this model is that we need an expression for the average fitness in the population. So P has some particular value. There's a mix of hawks and doves. We've got an expression for the average fitness of hawks in a mixed population. And we've got an expression for the average fitness of doves in the population. It's these two things I'm pointing at. Now we need an expression that uses them both to get the average across all the hawks and doves. And all that means is we apply our axioms of probability. And so P of the population is hawks, and the fitness of a hawk is this. Yeah? Hawks. Yeah? So the weight of P of the population gets this value. And yes, it's P times P, and the 1 minus P. It's just, the math demands it. Yeah? And 1 minus P of the population is doves, and they get 1 minus P, P over 2. So that's really 1 minus P, 1 minus P. Yeah? Good times. Yeah. Again, the math demands it. And now we ask, what value, let me say this is doves. What value of P would maximize this? Okay, so the orthodox way to do this, which is not what we're going to do, the orthodox way to do this would be to take a derivative, right? So we have a function, it's a function of P. I'm asking you what value of P maximizes this thing. That's a calculus problem. Yeah, those of you. You solved a bunch of insufferable calculus problems about the shape, volumes of tin cans and things like that. Some helping with calculus. Yeah, and yeah, so I'm not going to do that to you. We're not going to do that. Instead, I think we can do this intuitively, purely intuitively. So let's imagine the extremes first. So imagine P were 0. There are no hawks. What's the value of this expression? I'll give you a moment to explore it with your eyeballs and think about that. Every place there's a P, there's a 0 now, a bunch of stuff cancels. You see it, it's happening before your eyes. Yeah? No? Somebody's nodding in that. Thank you. That's humoring me. And, well, if there are no hawks, then everybody's a dove, right? And the only thing that's left is this V over 2 on the end. It's V over 2. The other extreme, P equals 1, it's all hawks. Yeah? Now the only thing that's left is this term, which sucks, right? V minus C over 2 is always less than V over 2 because there's a cost of injury. Injury effectively depletes the value of the resource, like burns it off into the atmosphere, right? The cost of injury. So the pure dove population has a higher growth rate than the pure hawk population. I've already proved to you that doves are never evolutionarily stable. Yeah? The next question is there some intermediate value of P which has a higher growth rate than V over 2? And the answer is no. And again, you could prove that with calculus, but I'm going to talk you through it. And in the notes, I show you the derivative, so if you're interested. But let me just talk you through it here. So imagine the first hawk. We're in the pure dove population, everybody's getting V over 2. Introduce one hawk. That hawk gets V. That's better than V over 2. Maybe mean fitness went up, right? Because it didn't get injured. It fought a single dove. The dove didn't get injured either. It got 0. But that pair, the first hawk and the first dove that fights a hawk, their average fitness is V over 2. It made no difference in the population growth rate. I'll say that again, because that was like a magic trick. Yeah, so the first hawk, the first hawk gets V because it fights a dove. And that's better than V over 2. So you get some hope like, oh, population growth rate might go up. But wait, the dove that it just took that resource from got 0. And so those two individuals have average fitness V over 2. And so the population growth rate has not gone up. It's a wash. You believe me? Okay, this is the non-calculus proof. There's calculus proof in the notes if you're interested. All right, now the second hawk. As soon as we add more than one hawk, they might meet one another. And now injuries happen. And then the population growth rate goes down because injuries deplete the value of the resource whenever they happen. If a hawk meets a dove, it makes no difference because dove and dove, one of them gets V and the other gets 0. Hawk and dove, one gets V, the other gets 0. So it makes no difference. The average fitness in those pairs is always V over 2. As soon as hawks meet one another, that's bad for population growth because injury depletes the value of the resource. You believe me now? That increasing P always decreases the population growth rate. And so this over here is where population growth rate is maximized, but that is never evolutionarily stable. Okay, so biologists are like, yeah, sure, that happens all the time. But again, there was a time in the history of evolutionary biology when this blew people's minds, that evolution by natural selection could lead to something that was not good for the survival of the organism. But this is a routine sort of thing that happens in the study of frequency dependence, and it's the reason we do evolutionary game theory. Even though evolutionary game theory, as a branch of applied mathematics, there's nothing unique about it. This is just dynamical systems theory disguised with a bunch of heuristics. Yeah, that's all it is. And that's the way I'm going to do this course. I'm going to disguise all the dynamical systems stuff for the most part with heuristics so that you can get the concepts. But we're going to do the mechanics. It's important to get used to the key skill that I want to instill in you over the next lectures is to be able to translate the biological narrative into these expressions. And that's the key skill. And then reducing them is something your computer can do for you. Yeah. Now, of course, it's good for you to do it yourself. I believe in the healing power of algebra. It's very, very, very good for you. But you can just Google derivatives now, right? And it just tells you the derivative of a function. We live in the future. Yeah. And sometimes it does give you the wrong answer, though, so you need to check. But does that make sense? What the motivation is here? It's the translation part that's super valuable. It's going from the scenario you have in mind. You have a question about a biological phenomenon. You make some clear statements about the consequences of behavior, and then you need to translate that into an algebraic system. And that's the skill I want you to get good at, so I'm going to show you a bunch of examples of doing that. Yeah? And then the math part, I'm going to do some algebra for you, but whatever, that's not the important part, because again, your computer can do that for you. It's the translation part that is a rare skill. Are there questions about this model? I'm going to do another one now.
Excuse me, do you have an estimate of P for that American rattlesnake?
What's that?
Do you have an estimate of P for rattlesnake?
Oh, no. This model is not detailed enough for that. I don't know what the consequences of what the V's and C's would be for a rattlesnake, but I think you could, models like this give you qualitative stuff in the sense that you can say that one system has larger C than another. And then you'd want to, if you wanted to test this model, you'd look at what's called the comparative statics. You'd see that the rank order of the frequencies of the amount of fighting is in the right rank order. That's the way you test it. But for precise quantitative predictions, I think these models are just hopeless. They just don't have enough stuff in them. There are exceptions in the theory of sex allocation, which is the evolutionary game theory about how many sons and daughters an organism should have. Those models make spot-on, accurate quantitative predictions for wasps, at least, right? So those are, parasitic wasps. This is the real biologist like this. Everybody else is like, what is he talking about? But parasitic wasps lay eggs in caterpillars, and wasps, like most Hymenoptera, males are just unfertilized eggs. And so the mom has complete control over sex ratio, right? It's like I wouldn't say it's a conscious decision because I don't know if a wasp is a conscious agent, but sure, why not? Let's imbue it with consciousness. And so, anyway, there's a game theory of all that, about whether you should lay a fertilized egg or an unfertilized egg in a caterpillar of a certain size. And the experiments bear it out perfectly. It's really amazing. But there's no other area of game theory I know which makes quantitative predictions that accurately. But the qualitative predictions are often good. Yeah. That said, when the qualitative predictions are violated, that's also good. Because the model is detailed and logical in a way that the direction of the deviation gives you clues about what's missing. And that's what's nice about these sort of non-null theory constructions, is that the theory violations are informative and they push us forward. So I'm big on testing this stuff, but you've got to think about it as qualitative, I think. Okay, in the remaining half hour, what I'd like to do is give you a glance at another strategy. So let's consider the possibility of retaliation. So there's a bunch of things you can do with this game to make it apply to different scenarios and answer additional questions. And there are several in the notes, and I'm not going to get to them all. One I think we have time to talk about is retaliation. So retaliation is the idea that you initially display, but if your opponent bears its weaponry and attacks you, you fight back. And the idea, the intuition, is that retaliation discourages conflict, right? It basically punishes aggression. But when retaliators meet, they get along, and they don't risk injury. Make sense? So we define a strategy called retaliator. And what does retaliator do? Display, but fight if attacked. Yeah? Does it make sense? So now let's take through the consequences. Can retaliator be evolutionarily stable against hawk and dove? This is the first question we're going to ask. So we think this through. The first thing we need to do to figure out if a strategy can be evolutionarily stable is to figure out how it does with itself. Right? A strategy that can't live with itself is not a good candidate for evolutionary stability. That was Hawk's problem. It has a problem living with itself. Yeah? Retaliator, what happens? Okay, so two retaliators meet, they display. As far as any one of them knows, the other's a dove. Right? So they display. One of them gets tired and leaves. The one that leaves gets 0. The one that stays gets V. V over 2. Good. We're off to a good start because that maximizes the population growth rate. Yeah? So this is good. So what we need now is to ask, is this greater than a rare strategy? So let's consider hawk first. A rare hawk is going to fight. The retaliator it meets is going to fight. So we need to know if V over 2 is greater than what the rare hawk gets, which is V minus C over 2. Food algebra with your eyeballs? Yeah? You prepared to tell me what this is? This true? Not a trick question. Yes, it's true. It's not, I know you're like, he's tricking me. I'm never going to trick you. That's not how I play. I don't trick students. It's not what I do. And again, to be a pedant, what's required is that C be greater than 0. Right? Yeah, if you really like to be injured, then this may not be satisfied. Yeah? Okay. So, retaliator is an ESS against hawk. So this is hawk retaliator H-R, and this is retaliator. Yeah? Now we need to do the same thing for a rare dove. What does a rare dove get? A rare dove gets V over 2. Right? Because dove and retaliator, retaliator basically mirrors its opponent's strategy, right? That's what it does when it faces a hawk or a dove. Yeah. So if it meets a dove, it acts like a dove. So then you see this expression, and you're like, and I ask you, is that true? And the answer is no. That is not true. So retaliator is not evolutionarily stable against dove. And what I'm going to draw out for you now is that this is very bad for it. It seems, the intuition lots of people have, at least humans, is that retaliation is a good strategy because it discourages aggression. At least in this scenario, which is not the real world, and it's not politics, and it's not human societies where people interact more than once. Remember, none of that's here yet. That's week 3. Yeah. The problem here is that retaliator does nothing to keep lazy doves out. Lazy doves do fine, and lazy doves are food for hawks. So what I want to draw out for you now is that there are evolutionary consequences of that in this game that make retaliator not such a great strategy. Yeah. And this already, just adding retaliator, makes the stupid model way more interesting. Lots of fun stuff happens that's counterintuitive. Okay. So the next question we need to ask. So retaliator is never evolutionarily stable because it does. It keeps hawks out. Okay, good. But doves can come in, and we don't know. Just mutational bias could make more doves drift, right? It's a finite population, even if it's large. Eventually, the frequencies of doves will fluctuate around. We're going to have to ask a question in a moment about what happens there. Because if there are a lot of doves, a rare hawk could probably invade because it won't need a retaliator, right? So we'll get to that, and we'll answer that question with mathematical precision. The first question I want to put before you, though, is to ask, could retaliator invade? Yeah? So, there are 2 scenarios. The first scenario, right here, retaliator invade, which means can it increase when rare? And there are two scenarios. In the first, V is greater than C. When V is greater than C, the first retaliator appears in a world of all hawks. And because V is greater than C, there are no doves. Yeah? There might be rare doves, right? But the selection pushes them back out again. You with me? And so we have to ask how a rare retaliator does against common hawks. So when a retaliator meets a hawk, yeah, or rather, we know what hawks get, right? D minus C over 2. We need to ask what a rare retaliator gets in a world of hawks. And what does it get? This is not a trick question. B minus C over 2, right? So I'm going to write it down. Rare retaliator is D minus C over 2. D minus C over 2. Which are the same. Selection does not keep retaliator out. Now, retaliator increases a little bit. You could think about it again. I think you can get this heuristically again. If retaliators are in small numbers and they ever meet one another, they do better. Yeah? When they meet hawks, they do exactly the same as hawks. There's no difference. No fitness difference at all. But whenever they meet one another, if they're in small numbers, they'll do better. And so selection will very weakly favor retaliator when it's rare. So it can invade a population of hawks when rare. You with me? Yeah? Some expressions. I'll say it again. So the first retaliator makes no difference. So this, it doesn't deterministically invade, but it can drift in. The first mutant appears, it's neutral. It's selectively neutral with the hawks. It's there. Maybe in small numbers, in families, you're near your kin, they're also retaliators, you interact with them, right? You don't fight. Then you do better. Yeah? We'll do families in week 4, I think it is. Then we'll make something formal about that statement. So retaliator can invade hawk and increase. At first, very, very slow, because there aren't very many and they don't meet one another very often, but eventually retaliator is common and they increase more quickly. We'll get to a point where retaliators are common, and then doves can invade. Right? Doves can't invade when hawks are common, because the doves get eaten by the hawks. But once retaliator is common and the hawks are gone, the doves can invade. So now we have to ask, if doves increase, how many doves do you need before hawks can invade again? I'll say that again. We have to ask, if doves can increase, because they're neutral with retaliator, once hawks are gone, how many doves can retaliator tolerate, in a sense, before the hawks are favored again? And we can ask that, and that's what we're going to ask algebraically. So, let Q, it's another symbol now, be Q be the frequency of retaliator. Remember, P was the frequency of hawk before. Now we're going to let Q be the frequency of retaliator. And we're going to imagine a bunch of worlds which are just retaliators and doves. So I'm going to draw another one of these lines. Yeah? So here's dove, here's retaliator, and this line segment is Q. If I have enough time at the end, I will put these two line segments together in one graph, and it will be a triangle. And we will have fun, but we may not get that far today, okay? This is the world now. Hawks are gone. Retaliator has chased them all the way, right? Retaliator is the police officer, right? But the police officer is not arresting the doves because the doves never start fights, right? So there's nothing going on here. And now the question is, when we're up here, doves can come in and they're drifting around, and if there's going to be some point on this line, this is my argument, I'll prove it in a second, when doves become common enough that hawks are favored again and they invade the population. And then everything goes to hell, unfortunately. Right? Then we're back to the hawk world, right? The cycle continues. Yeah? So we can find that. We just have to write average expressions. Okay? So what, when the population is only retaliators and doves, everybody's getting V over 2. So there's no math to do. Right? For hawk to invade, it needs to do better than V over 2, because that's what every retaliator and every dove gets on average in a population with only retaliators and doves. Yes? I know there's a bunch of stuff flying around here. This is how it is. The only thing we got to figure out is what that rare hawk does now. A hawk appears it faces a proportion Q of retaliators. That's the frequency of the police officers. Yeah? And so the question is, what happens to which values of Q allow Hawk to invade the population? So we need to write an expression for the average fitness of Hawk that has Q in it. Yeah? So this is what we do. We say, Q of the time, the Hawk meets a retaliator. Yeah? Put yourself in the shoes, if this helps, this doesn't help everybody. Put yourselves in the shoes of this rare retaliator. Rare Hawk. You're the first Hawk, you're coming up to a resource, there's another animal there, and you're like, oh, I wonder, is that a retaliator? Well, Q of the time it will be. Yeah? And then we write down the consequences of those interactions. And the consequence of that is V minus C over 2. Yeah, because it starts, the retaliator does a little display, and then you attack, and then you get in a fight, and you risk injury. Yeah? Or, the other individual is a dove, and that happens 1 minus Q of the time. In which case, you get V, which is what every Hawk wants, really. And we want to know when this is greater than V over 2. Because when this is greater than V over 2, a rare Hawk can increase. So that's the hard part. It's that translation exercise. That's the skill that you want to learn if you want to think about models. And also if you want to read and critique other people's models, instead of just skip that section in the paper, right? Just kind of hum. Okay, results. Right? If you really want to interrogate other people's models, you don't need to repeat their algebra. What you need to do is interrogate the setup and see that the logical assumptions make sense in the expressions that are given. That's what good peer review modeling is about. Yeah, because the computer can do the algebra. What you want to check is that the setups make sense. This is also a way to, you get good at this and you can read the assumptions off these things. You get fast with it. Okay, so we can do this. Let's reduce it. So again, I'm going to get rid of the fractions because they offend me. And I'm going to group the Q's together. So we've got V minus C Q's, and we've got minus 2V over there. And it has to be greater than V over 2 minus V. Yeah, so this is going to be minus V minus C greater than minus.
Yeah, there's,
that 2 that went away, didn't it? So this is, that became V and this became 2V, it's minus 2V. Yeah, so it's minus V. Yep. Told you, blackboard radiation. Yeah. And so this implies the threshold Q is less than V over V plus C. So again, some point on here, V over V plus C, and if we're below that, Hawk increases. So this is the, I think the kids call it the danger zone. It's a movie? No, it's Top Gun. And this is the region up here where retaliator is common enough that a rare Hawk can't increase. But down here, it will increase. Yeah, selection will favor it. And it will increase and it will eat up the doves until there are so few doves that Hawk gets pushed out again. And then you're back to a common retaliator world, and then the cycle can continue forever. And in a model like this, you can spend a lot of time here. Yeah, waiting for drift or some other force to increase the number of doves. But you're not in any kind of equilibrium here. Yeah. The other thing that could happen is that V is less than C. Now I'm going to wave my hand about this. It's in the notes. I show you how to do this. If V is less than C, what you want to ask is, can retaliator invade the mixed equilibrium of Hawk and Dove? Because when V is less than C, the first retaliator isn't going to face a world of all Hawks. It's going to face a world with V over C Hawks, right? And 1 minus V over C Doves. Why V over C Hawks? Because we're here. Yeah? So that's the point it needs to invade. Yeah? And I show you in the notes that it cannot do that. It cannot invade that mixed equilibrium. There's proof in the notes. I've got 15 minutes and I want to do some like concluding fanfare here. But yeah, explain your homework problem. But it's in the notes, and if you have questions about it, I'm happy to answer them next time. I mean, one of the reasons Retaliator, in all cases, the fatal flaw of the Retaliator is it tolerates doves. And at the mixed equilibrium, the reason it has a hard time invading is because so at the mixed equilibrium, hawk and dove have the same fitness, even though there's a bunch of fighting going on. Retaliator comes in, and it gets into fights with all the hawks, and it doesn't take advantage of the doves. So hawk has the same fitness as dove at the mixed equilibrium because it's eating doves, but Retaliator never eats a dove. And so it has lower fitness at the mixed equilibrium. That was the heuristic version of the argument. Yeah? When Retaliator is common, its flaw is that it tolerates doves, and as doves increase, that encourages hawks to appear again. When Retaliator is rare, it doesn't take advantage of doves. It's too nice, and so it can't increase. Poor Retaliator. No, we shouldn't moralize this. This is all about exploring the scenario logically, right? And obviously in a society where the strategies are learned, the dynamics could be different, because then you've got to figure out how that learning works and the reinforcement and whether the goal is your individual fitness or not, right? So all kinds of interesting questions about that when you add learning to game theory. But we're not going to do that. We're going to start simple and get it through. Questions? Good? Okay. Also in the notes, I mentioned two other strategies, which will not be in your homework. I'm going to just mention these to you so that you can take a look, so that you're maybe interested in looking at the notes and seeing. The first is called assessor. What does assessor do? Assessor looks at its opponent and tries to figure out whether its opponent is bigger than it. Seems like a good idea. Yeah? And when assessor is bigger than its opponent, it plays hawk. And when it's smaller than its opponent, it plays dove, meaning it displays. And the reason this can help assessor is because we assume that in the simple version of the model, obviously size is a continuous variable. But let's just imagine that all that matters is who's bigger or smaller. It's just the asymmetry that matters. And for the simple version of the model, then, you can just say that the larger individual wins with probability x. Not 1/2, but x, which is greater than 1/2. And so that means when assessor fights a hawk, so just as an example, when assessor fights a hawk, what does it get? Half the time it's larger. Yeah, that's what I'm going to write. Half the time it's larger than its opponent. And so it doesn't get v minus c over 2. Instead it gets xv minus 1 minus xc. And x is greater than 1/2. So it's picking its fights wisely. Well, we don't know if it's wise yet. Right? We haven't explored the evolutionary dynamics. But this is smarter than hawk, right? Because hawk just always fights. Yeah? The hawk, it's the flip side. The hawk gets v1 minus x at a time, because the hawk is smaller. What happens when assessor is smaller? Well, it bravely runs away. Yeah? Because it's at a disadvantage. Anyway, it turns out if x is large enough, then assessor can be evolutionarily stable against hawk. But it depends upon the value of the resource and the cost of injury. Okay, and that's in the notes. This is something, there was a question about testing before. The assessor model has been empirically tested with spiders, with territorial spiders, hunting spiders. And they do assessment. And if their body sizes are really similar, though, they do something else. Because when x has to be large enough, which is like saying the size asymmetry has to be predictive enough for you to use it to decide whether you fight or not. If the two spiders are similar enough in size, the logic goes, they might want to do something else. There's a spider biologist, Susan Reichert, who has done cool like arena experiments with hunting spiders on this topic. And they're vicious little things, just vicious. And things my cat eats, right? These little hunting spiders, they're delicious, he thinks. And so what happens in those circumstances is instead, there's a bunch of strategies which use convention. What's a convention? A convention is a cue. So size is a cue. Assessor uses a cue. It uses body size, or any other cue fighting ability would work too, but size is a very good one in animal societies, right? And a convention is some cue that has no relationship at all to fighting ability. But if the competitors agree to use it to decide the conflict, it turns out it can be evolutionarily stable. And you could pick a bunch of cues. They could be completely arbitrary, actually, all kinds of stuff. Coin flip would work, right? Think about the dumbest sort of things you could do. You could just flip a coin. It's like, okay, we both want this thing, let's face it. We don't want to get into a fight. Let's just flip a coin. That's a convention. Yeah? What's another convention that might be available for animals that can't flip coins, right? Hawks and doves don't have hands. They can't flip coins. So what are they? Thank you for laughing. Somebody laughed. So, the one that's discussed a lot in the biology literature is order of arrival. Who was there first? Yeah? And so if who arrives first is just a convention. It doesn't necessarily have anything to do with fighting ability. Just because, you're arriving second, maybe you're bigger than the other individual. Maybe you could take the spot from them, right? But if you have a strategy that uses order of arrival to decide whether to fight or display, it turns out it can be evolutionarily stable against hawk and dove. And I show you that in the notes, time to prove it to you. And it can also invade when rare, which is the weirdest thing, right? And the reason is because when it faces hawks and doves, it still just gets V over 2 all the time. So it's doing fine. When it meets itself, it never fights, right? It never gets into an injury. And that's the thing. The convention is a way to escape wasting the value of the resource on injury. The weird stuff, though, is that almost any convention will work. And so who arrives second works just as well as who arrives first, right? And so John Maynard Smith, who's this British evolutionary biologist who was one of the original definers of evolutionary game theory, he called the first convention bourgeois, because he was a communist, right? So he was making fun of the middle class. He called them bourgeois. And the other one, anarchist. So bourgeois respects property rights. This is John Maynard Smith being a pinko. He was like this in all his papers. He says, so bourgeois respects property rights, and so whoever was there first owns the resource. And anarchist is the opposite. The anarchist says that property is theft. So the second one attacks. And both of them have exactly the same evolutionary dynamics, which is obviously stupid, right? Because in the real world, that can't be true. They're really different things. But that just means there's lots of stuff missing from the model. And that's an opportunity to put something else in and think about it. Yeah, the value of the stupid models. Okay, I show you how to construct the fitness expressions for the convention in the end of the notes too, if you're interested. If you have questions, let me know. It's my job to expose you to this stuff. And there's a huge literature on thinking about contests and in repeat games and stuff like that. We could think about repeated contests in week 3. Each week, I want to give you one homework problem. Just one. And those of you who are willing to do it and turn it into me, whether it's right or not, wrong is full credit. I just need to see you try it. If you do them all 5 weeks, then you get your one credit point for the course, okay? It'll be, what you'll get even more than that is the growth of your soul. It will be very good. Your humanity will swell. Yeah, under the power of it. No, okay. So for the first practice problem is actually in the notes, but I'm going to talk about it here for you before you go, so there's no ambiguity. What I want you to do is add display costs. So what I want you to assume is that when 2 doves meet, we're going to rewrite the payoff matrix for you. So nothing new with hawk and hawk. Nothing new with hawk and dove. What's new is when doves and doves meet. So we're going to assume that the display has a cost. It costs you time and energy, right? And that's not nothing. When doves meet hawks, they don't pay that cost because they retreat. Yeah? So they don't pay the cost when they fight a hawk. But when they fight one another, they do. And so, what you get is b over 2 minus little d, where d is the display cost. Greater than 0. Yeah? Less than c. Yeah. It's not as bad as getting injured. And I want you to rederive the evolutionary dynamics of hawk dove game with that one change in place, which will require you to review the notes. Yeah, you know what you need to do. You'll have fun. Yeah, question?
Sorry, where are the notes?
There, I erased it. There was a...
Yeah, sorry, I missed the start of the...
That's okay. That's a great question. Thank you. There's a course website that has the notes on it, and I'll keep updating. And I'll put solutions there too when we get to them. And it's GitHub RMCELREATH. That's my name. Yeah, sorry. Blame Scotland. Don't blame me. Right. And then the course name is VLEGT, Very Little Evolutionary Game Theory. Okay. And there's PDF notes there, and I'll keep updating that. And assuming this recording works, I'll put that there too. Okay. Is the homework problem clear? Yeah. I mean, you got to do it, but that's the whole setup. Okay. Okay. Thank you all very much. Go eat.